Question 2.1. Describe how molecules are ionised using electrospray ionisation. So this is in a time-of-flight mass spectrometer. Well, first of all, you've got to purify the liquid sample. It needs to be dissolved in something that's polar, a volatile solvent, such as water or methanol. So it's going to be dissolved in something like water or methanol. Polar, so that it will dissolve in it. Volatile, so that it will have a low boiling point. The solution is pumped through a hypodermic capillary needle, so it goes through a very fine needle, and the sample is converted into a fine mist. And when it comes out of that needle as a fine mist, a very high voltage is applied to the tip of the capillary, and that forces each of the particles to lose an electron and form a plus charged fine droplet of liquid. Give the formula ion that reaches the detector first on the time-of-flight mass spectrometer. It's going to be the lightest one. So if you calculate the MR of each of these particles here, molecules, then C3H5O2N is the one with the lowest MR, the lightest one. Sample of germanium is analysed, given an equation using state symbol for the process that occurs during the ionisation of a germanium atom. Well, it's the first ionisation energy, so you've got a germanium atom GE. It's got to be gaseous. We've already determined that it comes out as a fine mist, so the liquid is made into a gas, into a fine mist, and then it loses one electron and forms GE+. It's still as a gas, and you've got to do the electron as an E- to balance the equation. 2.4. So you've been given a lot of information. So in a time-of-flight mass spectrometer, you should know, it's given here, kinetic energy is half mv squared. So kinetic energy is half mv squared, and the kinetic energy is given to you here, kinetic energy 4.238 times 10 to the minus 15. So that equals half mv squared. So what I've done is I've multiplied both sides by 2 and to get mv squared, and then the length or the distance is 96 centimetres. That tells you here 96.00 centimetres. You need to convert that into metres, 0.96 metres. So this is another equation you've got to learn quite often. You're not given this, that velocity is distance over time. If you think about driving a car, and your speed or velocity is in miles per hour, miles is a measure of distance, hours is a measure of time. So speed or velocity is distance divided by time. So the distance that's travelled is 0.96 metres. I've got that into metres. The time, it tells you here, somewhere it tells you time reaches the detector in 4.65 times 10 to the minus 6 seconds. That's correct. It should be in seconds. 206,274 is the velocity. So v squared is this value squared, 4.25 times 10 to the power of 10. So now I can substitute this in. So now I can work out mass here, because I've got v squared, I've got kinetic energy, I can work out mass. So it's the mass is 1.147 times 10 to the minus 25, and that's the mass of one particle. It's one particle in kilograms, so if I multiply by Avogadro's number, it gives me the mass of a mole, 6.91 times 10 to the minus 2 kilograms, multiplied by 1,000, 69.1 grams is the mass of 1 mole of this substance. Question 3.1. Complete the full electron configuration of the chromium atom. Now, chromium has got an atomic number of 24, so it's got 24 electrons and 24 protons as well. But it does something slightly odd. So 1s2, 2s2, 2p6, 3s2, 3p6 isn't unusual. Then you might be tempted to put 4s2, 3d4, but what it does is it half fills its 3d shell by taking one of the electrons from the 4s. So filling up its 3d shell, half filling its 3d shell and half filling its 4s shell makes it stable. So it takes one from the 4s and puts it into the 3d to half fill the 3d. Question 3.2. An atom has 2 more protons and 3 more neutrons than an atom of 5224 Cr. I know if it's got a symbol chromium, it's got a atomic number of 24. So if it's got an atomic number of 24, it's got 24 protons and 24 electrons because it's an atom, not an ion. But then what I can work out is from 24, 52 take away 24 is 28. So the remaining mass is 28. The only other subatomic particle in there that has any mass is a neutron, so that's 28 neutrons, so it's 24, 28N. It says that it gets 2 more protons, so it's going to go up to 26 protons, and 3 more neutrons, so it's going to go up to 31 neutrons, so it's 31, 26 something. Now the bottom number, the atomic number, determines what atom it is. Never look up 26, that's Fe. A sample of chromium contains 4 isotopes and has a relative atomic mass of 52.09. The reason it's an odd number is because it's an average of all of the isotopes. So now it shows the mass number and percentage abundance, that means how common it is, of 3 of these isotopes. I've got an isotope mass number 52, 53 and 54. Determine the percentage abundance of the 4th isotope. So there's a 4th isotope that I don't know anything about. One thing I can do is I can work out the percentage abundance. So if I add these all up, then the missing amount, the missing percentage that is, so 100, subtract these 3 numbers here, 82.8, 10.9 and 2.7 will tell me the missing percentage of the final isotope. I don't know its mass. So 100 take away 82.8, take away 10.9, take away 2.7. I've got 3.6% of another isotope. So the calculation then, imagine you've got 100 atoms. That's always a good step to start off with. So out of the 100 atoms, percentages is amount out of 100, 82.8 have got mass 52, 10.9 particles, atoms out of the 100 have got mass 53, 2.7 of the particles out of the 100 have got mass 54, and 3.6% of the remaining isotope, I don't know what its mass is, and so I'm going to call it mass Y. So the total mass is 82.8 particles times 52, that's the mass of those, 10.9 particles of mass 53, multiply those two together, 2.7 times 54, that's the mass of those particles, and 3.6 particles out of the 100 have got mass Y, 3.6Y. The total mass is therefore, if I add everything up, it's 5029.1, add 3.6y. That's the total mass. So an average is the total mass divided by the number of particles, and this is where your 100 atoms comes in. So that's the total mass divided by 100 gives me the average. Now I know what the average is, it's 52.08, so 5029.1 add 3.6y divided by 100, which is my average, equals 52.09 from here. If I multiply both sides by 100, 5209 equals 5029.1, add 36y, subtract 5029.1 from each side, equals 3.6y. 3.6y is 179.9, divide by 3.6, 49.97. So that's the mass number. Now all the other mass numbers are to 2 significant figures, so I'm going to round it up to 50. So my missing mass number is 50. Deduce the oxidation state of chromium in Cr2O72-. So a good reference point is oxygen. Oxygen's in group 6 of the periodic table, gains 2 electrons. Gaining 2 electrons, it's got an oxidation state of -2. That's a perfect reference point. So 7 minus 2 is a minus 14, so the O's contribute minus 14. The 2 CRs must be plus 12, because 12 plus 12 minus 14 leaves the 2 minus left over. So the CR2, the 2 CRs, have got a combined oxidation state of plus 12, so each chromium must be plus 6. Iodide ions can be oxidized to iodine using these ions. Deduce a half equation. So a half equation is just part of the equation. It's always got electrons in there. So iodide ions are I-, iodine is I2. I minus to I2, I'm going to need two I's, two I minuses to make the I2, and let's balance up the charges with electrons. Remember, half equations, you've always got electrons, two minuses on the left, so I need two electrons on the right. Deduce the half equation for the conversion of acidic solution. That's a clue there, acidic solution. Acids always have H pluses, so if you can't balance something, say for example Cr2 plus O72 minus to Cr3 plus, where are the O's going? Well, the answer is you can always add H pluses, and the acidic solution has kind of prompted you to that. You can always add H pluses, and you can always make water H2O, so that will always help you balance it. So I've got CrO72 minus. I'm adding some H pluses to the left hand side, because the H pluses and the O's will make water, which I've added to the right hand side. Now this looks complicated, but it's not really. Forget about the electrons for now. Where's the 14 come from? Well, Cr2O72 minus plus H plus make Cr3 plus, it tells you that, and H2O. I've got two Crs here, so I need two Crs here. I've got 7 O's, so I need 7 H2O's. 7 H2's are 14 H's, 14 H pluses. Now let's add up the charges. I know it's a half equation, so I'm going to need electrons. 2 minuses and 14 pluses leave 12 pluses on this side. 3 pluses are 6 pluses on this side, so I've got 12 pluses on the left, only 6 pluses on the right, so 6 electrons will mean that I've got 6 pluses on each side. Use your answers to deduce the overall redox equation. So what you do is to combine two redox equations, I have to balance the electrons. And to balance the electrons, when I add everything on the left of each equation and everything on the right of each equation, the two electrons must balance and cancel each other out. Now they're never going to balance, because I've got 6 electrons in this one and 2 electrons in that one. So I'm going to multiply everything through by 3 on this top equation. So 2I minus becomes 6I minus, I2 becomes 3I2, and 2E minuses become 6E minus. Then I take everything from the left and everything from the right. So I've got 6I minus because I multiplied this through by 3. Cr2O72 minus, 14 H pluses and 6 electrons, and then everything on the right, I multiplied this through by 3, so I've got 3I2, 6 electrons, 2 Cr3 pluses and 7 waters, and now you can see why I've multiplied this through by 3 to get 6 electrons on the right hand side. The electrons cancel, and so once my electrons cancel, I end up with a simplified equation like this. Question 4. The first ionisation energies, that's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms under standard conditions, increases, or well, it doesn't say that, but it will, energies the elements in period 2 change as the atomic number increases. Explain the pattern in the first ionisation energies of the elements from lithium across to neon. So the first thing you've got to say for 6 marks, for the first mark, is that across the period the ionisation energy increases on the whole, generally. That's because the atoms get more protons, so increased atomic number, increase in proton number, more protons, so increased nuclear attraction for the electrons that are there. There's no difference in shielding, they've got the same number of electron shells. And then you've got to explain the anomalies then. So boron, 1s2, 2s2, 2p1, it's got this 2p1 electron. So boron is in group 3 of the periodic table. It's got 2s2, 2p1, and that p electron is further from the nucleus than the 2s electrons, and therefore it needs less energy to remove that electron than it would do the 2s electrons. So less energy means that it's got a lower first ionisation energy than you'd expect. Then you get to oxygen. So oxygen's in group 6, it's got 2s2, 2p4. Now the p level is full when you get 6 electrons, so therefore it's half full when you get 3 electrons. When you get 2p3, 3 electrons in the 2p level, it's half full. And those electrons are not paired up, they're single electrons in different orbitals. But when you get a 4th electron in there, it pairs up with one of the other 3 electrons, and that causes it to repel. And when it repels, it's more easily removed, so it's repelling one of the other electrons that's just paired up with. And so it's more easily removed, and therefore that has a lower first ionisation energy than than previously when the 2p3 electrons, when the 3 electrons were unpaired. Question 5.1. It looks as if you've got an equilibrium reaction. You've got amounts of each of the substances before you've mixed them, before it's reached equilibrium, and then some of the amounts in the equilibrium mixture, and you've got to work out the remaining amounts. Fairly standard question. I always set it out as a table because I think it's easier to see. So I put it as a table and I put the three chemicals, the NO, that should say Cl2 rather than O2, sorry, and NOCl here. I put at the start, it tells me that I've got 1.5 moles of NO, 1 mole of Cl2 here, and 0 moles. It doesn't have any mention of this, and you've not made any of this yet because you're only just about to mix them, so that's 0. It says at the end, the equilibrium mixture contains 0.35 moles of NOCl. It asks you to work out the other two, so how on earth can we do that? Well, if 0.35 moles of NOCl have been made, we can work out what it's been made from. So it's used up some of the reactants here to make the product. So 2 moles of NO make 2 moles of NOCl, so the same number of moles of NO are used up to make the same number of moles of NOCl. So 2 moles of NO would react to make 2 moles of NOCl. So if 0.35 moles of NOCl are made, then 0.35 moles of NO are used up. How much Cl2 is used up? Well, 2 moles of NO react with 1 mole of Cl2, 2 to 1, so 0.35 divided by 2, 0.175 moles of Cl2 have been used up. Therefore, work out how much is at equilibrium. I started with 1.5 moles of NO, I've used up 0.35, subtract the 2, 1.15 moles of NO remains. How much Cl2 remains? I started with 1, I've used up 0.175, subtract the 2, 0.825 moles of Cl2 have been used up. NOCl, well, I just made 0.35 moles of that, and it's not asking me that in the question because I just made that. So amounts of NO 1.15, amounts of Cl2 0.825. There are your answers. Give the expression for Kc. So it's NOCl on the right hand side, the concentration of it, raised to the power 2, that's the number of moles in front, divided by concentrations of the chemicals on the left, the reactants, NO to the power 2, that's number in front, Cl2 to the power 1, so you can leave that off, and the square brackets and concentrations. Now it says at a different temperature I've got different amounts, it just wants me to put them in. So I've got the equilibrium expression from before, it gives me the Kc, the equilibrium constant, 1.32 times 10 to the minus 2. It tells me the concentrations of NO and it tells me the concentrations of Cl2, so I've put those in, and then I've multiplied 0.85 by 0.85 because it's squared, multiplied by 0.58 equals 0.331. I've multiplied both sides by 0.331, so my NO2Cl concentration squared of these two numbers multiplied by together, square root it, NOCl is 0.066. Question 6, I've got a diprotic acid, H2A. Diprotic acid means that 1 mole of the acid, one of these, reacts with 2 moles of something like sodium hydroxide, which is a base or an alkali, so 1 to 2. That's going to be important later on in my calculation, I'm sure. 25 centimetres cubed of aqueous solution are prepared using 1,300 milligrams of H2A. Remember, you hardly ever use milligrams, you convert it to grams, so I'm going to divide that by 1,000, I feel, and end up with 1.3 grams at some point. A pipette is used to prepare 25 centimetres cubed of 0.112 moles aqueous sodium hydroxide into a conical flask, and then we get a titration. Use the results to calculate the MR of H2A. So, first of all, I can do something with the sodium hydroxide, because I've got two values for the sodium hydroxide before. So, before I start working out titrations results here, I know that a pipette is used to have 25 centimetres cubed, which is 0.025 decimetre cubed, of 0.112 mole decimetre cubed sodium hydroxide. Concentration is 0.112, volume 25 centimetre cubed, always got to get volume into decimetre cubed for for calculations. Concentration is moles divided by volume. Concentration 0.112 is moles divided by 0.025. Multiply both sides by 0.025. I've got the number of moles, 0.0028 of sodium hydroxide. Now that's in the conical flask. The same number of moles, no, that's wrong. Half the number of moles, because it's diprotic acid, it would be the same number of moles of acid would react. But because it's a diprotic acid, 1 mole of diprotic acid react with 2 moles of sodium hydroxide, in other words half the amount. So the number of moles of the diprotic acid neutralized is 0.0028 divided by 2, because 1 acid react with 2 sodium hydroxide. 0.0014 moles of the diprotic acid, this H2A, this fictitious acid, is reacting. Now I come to my results. I've got to look to it for the best 2 results. The best 2 results are called concordant results, and more accurately it means that they're no more than 0.1 centimetre cubed apart. So I'm looking for 2 of the closest here, 2 that are less than 0.1 apart. If you end up with 3, by the way, I use all 3, but I've only got 2. Titration 1, 26.40 and 26.50 from titration 3 are 0.1 apart. 26.75 is 0.25 away from titration 3, and the rough ones much further apart. So I'm going to use titration 1 and 2, and I work out an average. 26.40, 26.50, add the 2 together, divide by the number of results, that's 2, so divide by 2, add them together, divide by 2, 26.45 centimetre cubed is the average from my 2 concordant results. So, I know how many moles I've used to react with the sodium hydroxide, that's 0.0014 moles, and that's in 26.45 centimetre cubed. So concentration is, I can work out here, I've got 0.0014 moles in 26.45 centimetre cubed, so I can work out by dividing by 26.45 centimetre cubed how many moles there are in 1 centimetre cubed, and then if I multiply by 250, I can work out how many moles that are in the 250 aqueous solution that I started out with. So I'll multiply by 250, 0.0132 moles are in this standard solution that I've made up at the beginning. So in the 250 centimetre cubed, I've now got 0.132 moles. Moles is mass divided by mol, 0.0132 is 1.3 grams. I said I'd have to convert this milligrams into grams at some point, divide by 1,000, 1.3 grams. Rearrange that equation, so MR is 1.3 divided by 0.0132, 98.5 to 3 significant figures. Most of the other values here are to 3 significant figures, so I'm going to go with 98.5, 3 significant figures. The uncertainty in using the pipette is 0.05. Remember, you're taking 2 readings though, so what actually happens is the error is 0.06 per reading. So because I'm taking 2 readings, a start reading, an initial volume and a final volume, I have to multiply by my error by 2, because every time I do a reading, that's the error that could occur. So 0.06 times 2 is 0.12, and then my percentage error is how far out it could be divided by my reading, which is my average of my 2 concordant results, 0.12 divided by 26.45, multiplied by 100% for a percentage, 0.45%. Before adding the solution, there's a bubble. At the end, there's no bubble. Explain why the air bubble increases the final burette reading. Well, some of it runs into the bubble rather than is dispensed from the burette. So some of it runs into the bubble before it actually starts dispensing. So no wonder you're getting a reading that's higher than expected. During the titration, the student washed the inside of the conical flask with some distilled water. Why is that okay? You'd never wash out the burette. You never wash out the burette because you dilute the solution. That's a standard solution that's in the burette. But you're allowed to wash out. In actual fact, it's good practice to wash anything down the conical flask. As you're swirling it, you should be washing the inside of it with some distilled water, because you're not changing the number of moles in the conical flask. The number of moles of sodium hydroxide is unchanged. Even adding water won't change the number of moles of sodium hydroxide. And so the number of moles of sodium hydroxide stays the same. Therefore, you can work out the number of moles of acid that you're adding, and from its volume and concentration, you can work out the concentration of the acid. Question 7.1. Magnesium is used in one of the stages in the extraction of titanium. Give an equation for the reaction between titanium 4 chloride and magnesium. State the role of magnesium in this reaction. It's a redox question. It's asking you about reduction and oxidation. First of all, you've got to work out what titanium 4 chloride is. So titanium, if it's in oxidation state 4, Cl always gains 1 electron. It's in group 7 of the periodic table. So most of the time it's in oxidation state -1 because it gains 1 electron. Not always, but it's a reasonable starting point. So that's in -1 oxidation state. 4 minuses, 4 minus 1 balances the +4. So the titanium's in +4 and Cl's are in -1. You're going to need 4 of them. Magnesium is Mg. It makes MgCl2. We know magnesium's in group 2, loses 2 electrons, +2 oxidation state. Cl -1, so 2 minus 1s to balance out the +2, so MgCl2. And it says it makes titanium. To extract titanium is to make titanium on its own, and you can need 2 Mgs to balance out the 4 Cls, which are on the left hand side. A mixture of magnesium oxide and magnesium hydroxide has a mass of 3,200 milligrams, or 3.2 grams. The mixture is reacted with carbon monoxide in the following equations. Calculate the percentage by mass of magnesium oxide in this mixture. So first of all, my first clue here is that the mass of water produced is 210 milligrams, divided by 1,000, 0.21 grams. Oh, sorry, the role of the magnesium is a reducing agent. The magnesium has gone from 0 oxidation state up to +2. It's been oxidized. The titanium's gone down from 4 down to 0, so that's been reduced. This is a reducing agent. The magnesium's been oxidized and in turn has reduced the titanium. Back to this one then. So the mass of the MgO and the MgOH2 combined, it says, is 3,200 milligrams or 3.2 grams. But more importantly, the water here, I've got a mass of water produced 210 milligrams divided by 1,000, I've got 0.21 grams. So moles of water is mass divided by MR. I can work out the MR of water, which is an oxygen, which is 16 and 2 ones for the 2 hydrogens, 0.0116 moles of water. And my water is produced here. So if I've got 0.1167 moles of water here, I've got equal numbers, 1, 1, 1 and 1. When you balance it, I've got an equal number of moles of MgOH2 reacting to make this amount of water. So if I've made 0.01167 moles of water, I've used MgOH2, I've used the same amount of same number of moles of MgOH2. So number of moles is 0.1167 is mass divided by MR. I've worked out the MR of MgOH2. It's a magnesium, which is 24, 2 16s for the 2 oxygens and 2 1s for the hydrogens. It's 58. Multiply both sides by 58. I've now worked out the mass of MgOH2 is 0.677 grams. Now I know the combined mass. It tells me the combined mass of the magnesium oxide and the magnesium hydroxide is 3.2 grams or 3,200 milligrams. So if I subtract the mass I've just worked out, the magnesium hydroxide, from this total mass, 3.2 grams take away 0.677 grams is 2.523 grams. That must be the remaining magnesium hydroxide. So I've got 2.52 grams of magnesium hydroxide. The question's asking the percentage by mass of magnesium oxide in the mixture. So 2.523 grams of magnesium oxide in the total mass of the mixture, which is 3.2 grams, divided by 3.2 grams, multiplied by 100%, 78.8%. I've put it to 3 significant figures because 210 milligrams is to 3 significant figures. This is to 4 significant figures, but always take the lowest data value, lowest number of figures from the question. 3 significant figures, so my answer's to 3 significant figures. Question 8, we've got some mixtures of compounds. We've got to distinguish between them by adding some reagents and say what we'd see. Sodium chloride and barium chloride. So The first clue is barium. Barium, if you make barium sulfate, it's a white solid, so you can make barium sulfate by adding sulfuric acid. We'll make barium sulfate. Sodium sulfate, that's made from sodium chloride, is soluble. All sodium salts are soluble, so there's no visible change there. But with barium chloride you get a white solid or a white precipitate of barium sulfate. Sodium chloride and sodium carbonate, well, you've got two choices here. If you added acidified silver nitrate, the silver nitrate will make silver chloride as a white precipitate or a white solid here. Silver chloride. You could then add, if you weren't sure, you could add dilute ammonia, which would dissolve the silver chloride. And actually then with acidified silver nitrate, normally you get silver carbonate, but if you acidify it, it will dissolve the carbonate, the silver carbonate, and it'll actually react with some of the sodium carbonate and make bubbles. The other alternative, of course, is to add any named acid like hydrochloric acid or sulfuric acid. It's going to have no change with sodium chloride, but with a carbonate it will make bubbles. So either of those two solutions will get you the marks. Question 9. Which sample measured at room temperature and pressure contains the greatest number of particles? Well, the number of particles in a mole is 6.022 times 10 to the power 23 Avogadro's constant. So if I work out the number of moles, and every mole has the same number of particles, we can change the question around by saying, therefore, whichever one has the greatest number of moles will have the greatest number of particles. So let's work out the number of moles. So to work out moles is mass divided by MR. MR of hydrogen H2 is 2, so 1 divided by 2, 0.5 moles of hydrogen in answer A. Helium has got a mass number of 4. Helium atoms are in group 8 or group 0. They've got full outer shells. They don't bond with anything. They've got an MR of 4. So moles is 1 divided by 4, 0.25 moles. And now here you need to know at room temperature and pressure, any gas, doesn't matter whether it's hydrogen or helium, 24 decimeter cubed is 1 mole. So 1 decimeter cubed is 24th, 1 divided by 24th of a mole. It doesn't matter whether it's hydrogen, helium or any other gas. So your answer is A, has the largest number of moles and therefore the largest number of particles. 5 grams of an oxide of molybdenum contains 4 grams of molybdenum. So I can look up the MR of molybdenum, 95.95. I can work out the number of moles of molybdenum in this oxide. Mass divided by MR is 4 divided by 95.95, 0.042. I know that there's 1 gram of oxygen in this oxide because there's 5 grams of the oxide and 4 grams of molybdenum, so 1 gram of the oxide. Moles is mass divided by MR. 1 divided by the mass of an oxygen atom is 16, 0.0625. So that's my ratio of molybdenum to oxygen. Divide by the small number, 0.042 divided by 0.42. I've got 1 molybdenum to a ratio of 0.0625 divided by 0.42 to 1.5 oxygen, 2 to 3, MO2O3, answer C. Question 11. Which substance has delocalized electrons? The answer to that is graphite, straight off. Graphite has delocalized electrons between the layers. That's what allows it to conduct electricity. Which species is not pyramidal in shape? Phosphorus is in group 5, so it's got 5 electrons in its outer shell. 3 bonding pairs, 1 lone pair, therefore, so it's going to be trigonal pyramid. H3O plus, oxygen's in group 6, loses 1 electron to form a plus. Means there's 5 in its outer shell, 3 bonding pairs, 1 lone pair, again trigonal pyramid. CH3 minus, carbon's in group 4, gains 1 to get a minus charge, means it's got 5 electrons, 3 bonding pairs, 1 lone pair, again trigonal pyramid. Whereas BF3, boron's in group 3, 3 electrons in its outer shell, 3 bonding pairs with the 3 Fs. It's going to be trigonal planar with a bond angle of 60. Which change occurs when water is vaporized? Intermolecular forces are overcome. That's what happens when something changes state. You break the intermolecular bonds between the particles. Question 14. Which equation represents the reaction which has a standard enthalpy change equal to the standard enthalpy of formation of barium chloride? So formation is making a mole of a compound from the elements as you'd find them in the laboratory in something called their standard state. So how you'd find them at room temperature and pressure. So barium in the barium chloride is a solid, so we're immediately looking for a solid. So we're looking for C. It's got to be elements, not ions, so your answer is C, and chlorine's a gas. So your answer automatically is C. Which equation does not represent a redox reaction? Straight off your answer is B, because that's combustion, oxidation by adding oxygen. Which property do you expect of the element radium? Well, radium's in group 2, they're called the alkaline earth metals. They're all metals in group 1 and group 2, and they're good conductors of electricity. Question 17. Which statement is not correct? A. Strontium has a lower first ionisation energy than calcium. Well, strontium's below calcium in group 2, so it's got more electrons, more shells. Electrons are further away from the nucleus, less nuclear attraction, more shielding, etc. So it's going to have a lower first ionisation energy, so A is correct. Strontium has a larger ionic radius than calcium. Again, yes, larger. More electrons, more shells, further away from the nucleus, a larger radius. Strontium reacts less vigorously with water. Now, as you go down the group, you get more and more reactive, so strontium will react more vigorously. Remember, if it's losing electrons, they're going to be more easily lost if they're further away from the nucleus, with more shielding and lower nuclear attraction. So C is incorrect. D. Strontium hydroxide is more soluble in water than calcium hydroxide. No, that is correct. Strontium hydroxide is more soluble as you go further up the group than the hydroxides become less soluble. So strontium hydroxide is more soluble as you go down the group. So your answer is C is not correct. Which property of the group 2 elements, calcium down to barium, increases with atomic number? Straight off atomic radius, we've discussed that already. As you go down a group, more electrons, more shells. Which is the best oxidizing agent? So you've got to remember what an oxidizing agent is. An oxidizing agent causes reduction. Oil rig reduction is gain of electrons. So F2 readily forms F-, so it's going from oxidation state 0 to -1. It's being reduced. Therefore, it's causing something else to be oxidized. It's a very good oxidizing agent. Your answer is A. Some fuel in the spirit burner is burned and the heat produced is used to heat a container of water. So this is delta H equals minus MC delta T. What is the amount of energy absorbed by the water? So you just remove the minus, so that's exothermic. Now we're talking about an endothermic reaction where heat is absorbed. So enthalpy heat absorbed is MC delta T, sometimes called Q. So it says here that the heat rise is Y. So if I substitute delta T, temperature change for Y, then I get MCY. My answer is A. The equation below represents the complete combustion of butane. 20 centimetre cubed of butane can burned in 0.2 decimetre cubed of oxygen, in other words 200 centimetre cubed. Which statement is correct? All volumes are measured at the same temperature and pressure. Let's work it out then. So for gases, the ratios of volumes reacting, the ratios of moles reacting, because whatever gas you've got, 24 decimetre cubed is 1 mole. So you can turn ratios of moles reacting into ratios of volumes reacting. So I could say that 1 to 6.5 makes 4 and makes 5. I could talk about moles, or I could talk about volumes in terms of ratios reacting here, as long as they're all gases. 20 centimetre cubed of butane are completely burned in 0.2 decimetre cubed of oxygen. Which statement is correct? So 20 centimetre cubed of butane would react with 6.5 times the volume of oxygen. So 6.5 times 20 is 130 volume of oxygen. So I'm going to react with 130 centimetre cubed of oxygen. So now then, I've got 0.2 decimetre cubed of oxygen, or 200 centimetre cubed of oxygen. I'm going to react at 130 centimetre cubed of it. I've got 70 centimetre cubed of oxygen remain. The answer is C. Question 22. Which statement is correct about reactions involving halide ions? So sodium chloride reacts with chlorine when, forms chlorine when added to concentrated sulfuric acid. No, it's going to make hydrochloric acid gas as white steamy fumes. Sodium chloride forms chlorine when added to bromine. No, there's going to be no reaction because chloride ion cannot be displaced by bromine. Bromine's less reactive than chlorine. C. Sodium bromide forms bromine when added to concentrated sulfuric acid. Yes, it will act as an oxidizing agent, sulfuric acid, and actually make bromine, so C is correct. Sodium bromide forms bromine when added to iodine. No, you're not going to get a displacement reaction. Iodine is less reactive than bromine, so your answer is C. What's the percentage yield when 20 grams of aluminium is produced from 50 grams of aluminium oxide? So if I look at 50 grams of aluminium oxide, if I work out the MR, aluminium is 27, so 2 27s and 3 16s is an MR of 102. Moles is mass, 50 grams divided by the 102, 0.49 moles of aluminium oxide. 2 moles makes 4, so twice as much aluminium, twice as many moles of aluminium are going to be produced. So I multiply the 0.49 by 2 and I work out that I've got 0.98 moles of aluminium being made. I'm going to turn that into grams, so moles is mass divided by MR, so 0.98 moles of aluminium is the mass divided by the MR of aluminium, which is 27. 0.98 times 27, I'm going to make 26.46 grams of aluminium. That's my theoretical, that's what I should make. So my percentage yield then is 20, that's what I did make, divided by my theoretical yield, 26.46 multiplied by 100%, 75.6%, 76% if you round it up. The answer is A. Monday the 20th of May 2019, paper 1 AS Chemistry. Question 1.1. Sodium fluoride contains sodium ions and fluoride ions. Na plus and F minus have the same electron configuration. Explain why a fluoride ion is larger than a sodium ion. Well, if both atoms have the same electron configuration, they've got the same number of electrons, same number of shells, so the same amount of shielding. Sodium has more protons, however, because the number of protons isn't changed, so it's got a greater nuclear attraction, therefore a smaller size. Explain in terms of structure and bonding why the melting point of sodium fluoride is high. Well, in sodium fluoride you've got Na plus and F minus, so they're oppositely charged ions. These attract strongly, that's called ionic bonding, and they're held in a regular ionic lattice, therefore a large amount of energy is going to be required to break these strong ionic bonds. H2F plus is formed when hydrogen fluoride gains a proton as shown in the equation. Name the type of bond formed when HF reacts with H plus. Well, H plus has got 1 electron and 1 proton. If it's plus, it's got no electrons now, so it's got no electrons to put into a bond. So the F donates both electrons into the bond, so it's called a dative or a coordinate bond. It's essentially a covalent bond. It's a shared pair of electrons between two atoms. However, both the electrons have come from the F atom, so both are from one of the atoms rather than each atom putting 1 electron in each. Shape of SbF 6-. Well, Sb is an element called antimony, and that's in group 5. It's got a minus, it's gained an electron, so group 5, 5 electrons in the outer shell, minus means it's gained 1, it's got 6 electrons in the outer shell. 6 F's come along and bond, so you've got 6 bonding pairs. 6 bonding pairs repel equally, and that's going to go into an octahedral shape with a bond angle of 90. H2F plus. F is in group 7. If it's plus, it's got 6 electrons in the outer shell. 2 of them bond to the 2 F's, and the remaining 6 electrons go in 2 lone pairs. 1, 2, 3, 4, 5, 6. So 2 lone pairs are going to repel most, so the lone pair repulsion is greatest, followed by lone pair, bonding pair, followed by bonding pair, bonding pair. So if it was 4 bonding pairs, it would be 109.5. Replace a bonding pair with a lone pair, it comes down by 2.5 down to 107 degrees. Another bonding pair replaced by a lone pair comes down by another 2.5 to 104.5. So it's bent or V-shaped, either of those will do. Bond enthalpies. Well, what you do for bond enthalpy, so the bond enthalpy, or the overall enthalpy, which is minus 179, equals the bond enthalpy of all of the reactants, so the strength of all the bonds on the left of the arrow, take away the bond enthalpy of the products, take away the bonds on the right. So what have I got here? So minus 179, which is the overall bond enthalpy, is the bond enthalpy of the reactants. That's a C to C triple bond in 837, 2 C to H's, which is 412. Added 2 lots of HF, 2 lots of 562. Take away any bonds on the right, so that's 1, 2, 3, 4 C to H's, so take away 4 times 412, and take away 2 times CF, 2 times 516. What's it trying to find out? Calculate a value for the bond enthalpy of the C to F bonds. Sorry, we don't know the C to F bonds, but the H to F bonds, sorry, we've not got the C to F bonds, so they're unknown here. We solved this calculation, and 2 to CF bonds is 1316 divided by 2. The C to F bond is 658. The bond enthalpies are always positive because it's the energy needed to be put in an endothermic reaction to break a bond.